Hi, my name is Chawit Aswachok. I recently completed my master's degree at University of Pennsylvania. I studied electrical engineering and worked as a research assistant under the supervision of Professor Cherry Kagan. I am starting my studies in Integrated Photonic and Electronic Systems program at University of Cambridge this fall. As a co-first author, I am going to share the work we carried out at Penn, which was published in the July 2015 issue of ACS Nano. This paper describes methods to dope colloidal lead selenide nanowires and to define p-n junctions that are used to demonstrate electronic and optoelectronic devices. We studied lead selenide nanowires because they have unique properties from those of other nanomaterials. As one-dimensional materials, they are quantum confined in their cross-sectional direction, but not along their length. This anisotropy in nanowire physical properties allows for higher mobility, carrier transport along the length, and absorption and emission polarization sensitivities. In particular, lead selenide nanowires are interesting as they have high electrical mobility, low thermal conductivity, and band gaps that are highly tunable through the near to mid-infrared. In this paper, we synthesized lead selenide nanowires by wet chemical methods that are low in cost and allow the preparation of small, quantum-confined, approximately 10 nanometer diameter wires, unlike wires grown from chemical vapor deposition. We fabricate devices by using electric field to direct the assembly of the nanowires from solution to form nanowire arrays that span the device electrodes. To make functional electronic and optoelectronic nanowire devices, we need to first dope our nanowires. Doping allowing us to modulate their electrical properties by controlling the carrier type and concentration. A major finding of this paper is that we developed stable N and P doping processes for colloidal lead selenide nanowires. We successfully N-doped the nanowires by introducing excess lead either by thermal evaporation and diffusion of elemental lead or by immersion of the nanowire array devices in a solution containing lead chloride. To introduce oxygen P-dopants, we exposed the sample to oxygen plasma. We control the dopant concentration by the dose of lead or oxygen created by these methods. We showed these processes are effective in doping nanowires, unlike bulk materials, as the atoms or ions introduced modify the nanowire surface remotely N or P doping. Utilizing these doping techniques, we then were able to make electronic and optoelectronic devices. By selectively doping one side of the nanowire P-type and the other side N-type, we created p-n junctions. By incorporating these concepts, we successfully fabricated high-performance CMOS inverter and fast-switching photodiodes. We used the P and N-type regions within the wire to create P and N-type field effect transistors and used them as the building blocks of CMOS inverters that show high gains of 15 for signal amplification and a near full signal swing for switching. We also use a p-n junction in the nanowire arrays to realize photodiodes that switch more than 1,000 times faster than that of photoconductors. Throughout our experiments, we came across several obstacles. One of them was to find a blocking layer to achieve selective N and P doping. We tested many different materials before finding PMMA was suitable. Another challenge that we faced was choosing the right self-assembled monolayers to treat our substrates. It is known that self-assembled monolayers such as acyl phosphonic acids and silanes are used in order to reduce the hysteresis in transistors. However, due to the very hydrophobic nature of these chemistries, the PMMA blocking layer poorly adhered. In the end, we chose MPTS as the surface chemistry for our nanowire device fabrication. To best of our knowledge, our work is the first report demonstrating colloidal nanowire integrated electronic circuits, and also the first example of colloidal p-n junction nanowire optoelectronic device. We further show that our selective doping processes for the lead selenide nanowire arrays are also compatible with device fabrication on flexible plastics. In the future, we look to fabricating single nanowire devices for low voltage, high speed, and high density circuits, and to scaling the device channel length to reduce carrier diffusion through the quasi-neutral regions to prepare higher performance photodiodes. The flexibility of selective doping also promises more complex device design and the construction of p-type intrinsic N-type junctions. Thank you.